Right, so it's a new chapter today. In the previous chapters, we talked about charges, electric force, electric field, and mainly we just looked at charges that are stationary, not moving. Now it is time to see what happens when they start moving. That is what is called current, electric current. Then something associated with the current is resistance. So the chapter title is current and resistance. So let's look at the content. Okay. Content, we have 8 sections. The last section is omitted. So 7 sections. We start with defining what electric current is. Okay, currents, when we say current, we mean electric current. So sometimes we will not say electric current, we will just say current. So you understand it is about electric current. Okay, there can be water current or some other current. Something that is flowing is a current. Okay, it can have water current. So here the charges that are flowing, we have electric current due to the flowing of charges. Topic 2, section 2, a microscopic view, when you go to the small scale and see what is a current and how it is related to the motion of the charges or the drift speed of the charges. And section 3, we will talk about measuring current and another thing called voltage in electric circuit, how we measure them in a circuit. Number 4, we introduce the new concept called resistance, resistivity, and Ohm's law, which connects the current with the potential difference or the voltage. Number 5, we will look at how resistance varies when we vary the temperature. So the variation of resistance with temperature. And number 6, electrical energy and power. Where we have energy, we have to talk about power. Power is how fast the energy is transferred. And then finally, superconductors is a new class of conductors, which is called the superconductors. As the name implies, actually the conductivity become infinite, or resistance of a superconductor is 0, the ideal case. Okay, so that is very important class. We will give a brief description of superconductors in section 7. Okay, so that is the content. Now let's go in. Right, current. Initially, the practical applications were based on static electricity. We charge something to a high charge, then there are some applications with static. Static means not moving, but eventually later there were new discoveries, and we were able to have moving electricity, which is current, and we were able to control that. And mainly after this battery was invented by a physicist, Italian physicist called Alessandro Volta. That is where the term volt comes to electricity. The potential difference is also called the voltage. Okay, that is from this, after this physicist who invented the battery in 1800. Battery is a device that can make charges flow in a circuit by applying a potential difference across the circuit. Steady source of electric current allowed scientists to learn how to control the flow of electric charges in circuit. So that was possible after the invention of the battery, which can give us a steady source of electric current through a circuit. Now let's define electric current. What is electric current? Current is to do with the motion of charges, which is actually the rate at which charge flows through a surface. That is what electric current is. More mathematically, the exact definition, the average current, we use the symbol I for current. We look at the charges flowing perpendicular to a surface area A, and we say the average current, suppose a current of charge of delta Q flows through this area A in a time of delta T, the average current is simply equal to the rate of flow of charges, delta Q divided by delta T. When you divide by the time, you are getting the time rate, okay? The charge flow per unit time. And you can see the unit is going to be, SI unit is going to be Coulomb, because charge is measured in Coulomb in SI. So divide by second. Second is the time unit for in SI. So Coulomb per second going to be the SI unit for measuring current. Now, as usual, we got a single name for Coulomb per second, ampere, and the symbol is A. So ampere is actually Coulomb per second. 1 Coulomb per second is 1 ampere. Right, is that all clear? Are you listening to me, please? Seem to be.
Yes, doctor.
Okay, thank you. Right, so that is what current is. So you got one formula here, the definition of current. So you should know this. You don't, if you are following with me, if you come along with me all the time and taking notes and absorbing what I'm saying, you don't have to study separately. You don't study just one day before the exam. So these are some definition. Okay, you just do it once and for all right now. That will save you a lot of trouble. Okay, it will be more efficient. So the current definition is the rate of flow of charges in a surface area. You look at how much charges flow, say delta Q, and take the time, say delta T, divide the charge, divide by delta T. That gives you the average current during that period. The SI unit is Coulomb per second, and Coulomb per second has the name ampere, after another scientist who worked along this line, okay, in electricity, as happens usually. Now, okay, that's the average current. Now, what about the instantaneous current? Like, we have velocity, what we did in semester 1, we defined the velocity as the rate of change of position. Okay, but during a finite time of interval, it will become average velocity. Then we define the instantaneous velocity. I don't want the exact value of the velocity at a moment in time. Like that, we can ask the same question. Okay, what about the instantaneous current? Not during a period of time, but I want the current at one particular point in time. So then we define the instantaneous current as the limit of the average current as the delta T goes to 0. So this is the instantaneous current. Suppose we have a steady flow of current, steady current, that means a current that does not change with time. I mean, a constant value of current. Then there is no difference between average and instantaneous. The instantaneous current will become the average current, okay, at any point in time during that period. Okay, so the unit will be the same as the average current, which is ampere or Coulomb per second. Okay, now let's look at the electric current in more detail. So what I said was the current will be, we look at a cross section and see how many charges are passing through this area, and the delta Q, amount of charge, divided by delta T will give me the current. So what about the direction of the current? Because the current can be due to positive charges flowing and the negative charges flowing. So we have to define the direction of the current. So the convention means people agree on a certain standard. The convention is the direction of the current is the direction positive charges would flow. So here in figure A, we show positive charges flowing to the right. So in that example, the direction of the current will be the same direction as the flow of charges because it is positive. Okay, this is a convention because we can have current due to negative charges flowing. Say, look at the figure B. In figure B, look, when you are listening to me, because I'm giving a lecture, okay, you should be following, you should be listening to me as well as looking at the screen. So it's two things, your eyes have to work, your ears have to work. Okay, that's you paying complete attention. So if you're only listening to me and doing something else, sometime I'll be referring to the picture. So you should be looking at the screen as well as listening to me, doing both. Are you? I'm asking you.
Yes, Doctor.
What about, yes, Abdullah, thank you. Right, thank you. At least two people responding. Thank you very much. So now, so figure A, thank you, Razan. So you see the convention is the direction of the positive charge flowing, but the current can be due to negative charge as well. It doesn't matter what is the sign. So what happens when a negative charge flows? So the convention is the direction of the current is in the direction of the positive charge flowing. So when a negative charge is flowing, the direction of the current will be opposite to the direction of the charges flowing. So that's why electrons, let's say electrons are flowing to the left, but we say the current is to the right. Suppose the electrons are flowing to the right, we'll say the current direction will be to the left. Okay, right, this is the convention. In a common conductor, copper wire, in electronic circuit, commonly we use copper. Copper is a metal and it is a conductor. The current is due to the motion of negative charges or positive charges. It's a question to you. How do you get the current in a conducting wire? Is it due to the positive charges moving inside the metal or negative charges moving inside that copper wire? Jude? Anyone knows? Guys, I need to know that you are listening. Otherwise, I have nobody here in the classroom. I'm in the classroom, okay? And no one is here, okay? So yeah, I need a response from you. Otherwise, I feel like talking to the walls. I better just end the class and go home. Yes, anyone? Jude,
Yes, Doctor.
can you answer me, please, Jude?
I'm sorry, can you repeat the question? I didn't comprehend it.
Okay, the question is, in a copper wire, which is a metal, suppose there's a current flowing. Current flow is due to the flow of charges. Now, in that particular example of a copper wire, when you have a current flowing, is it the negative charges flowing or positive charges flowing?
It's the negative charges flowing, right?
Yeah, because metal have free electrons. Positive charges mean we don't have any ions or anything that can flow in a metallic solid wire. So protons are fixed to the nucleus. They are not free to move. Only the electron, which are the free electrons, because conductors have free electrons, the valence electron and the outermost electron, they are free to move. We have these free electrons, which is free to move. It doesn't belong to any one particular lattice atom. So these are the one that move. So in a common conductor such as copper, the current is due to the motion of negatively charged electrons. Okay, so the negative charges that are moving. We call those moving charges, which is free to move, as the mobile charge carrier. So there are some terminology that you should know, okay? Because we can have question, not only numerical question, we can also have definition statement questions. So the terminology is important. Otherwise, you cannot talk to your colleagues, okay, in a work area. So you cannot just describe things. You have names. You should know the names. So moving charges are called the mobile. Mobile mean moving, right? Mobile charge carrier. The charge carrier can be positive or negative. So in this example of a metallic conductor, the charge carrier is the electron, which is negative. But you can also have charge carriers positive, like in a solution, say sodium chloride solution, the ions, the sodium ions can be moving around, moving to a certain direction. That's a current due to a positive charge. Okay, so it's possible to have a positive mobile carrier, a mobile charge carrier. Right. Now, okay, thank you, Abdulaziz. Okay, yeah, you've done good in the exam, Abdulaziz. Okay, the exam result I will release maybe later in the night. Okay, evening. Power. In a conductor carrying a current, the electric potential of the charges is continuously decreasing. So that's what happened. Maybe one of the question in the exam was a statement question. Always the charges move to reduce its potential energy, right? It moves from, when it moves, it is to move such that to reduce its potential energy. Whether it doesn't matter, negative charge or positive charge. The potential, okay, positive charge will move from higher potential to lower potential. Negative charges will move from lower potential to high potential. Okay, so it's two different things: potential and potential energy. Positive charges move from region of high potential to region of low potential. So you can see that. So this is a positive. I'm talking about positive charges, and since positive charges move from higher potential to lower potential. Okay, Jude. Yeah, you did well too. Okay, but I'm talking relatively. Okay, yeah. Okay, but there are people who did well, and there are people who may brought the average low, unfortunately. But yeah, this is life. Okay, you always have an average, and some people above average, some people below average. Okay, fine. So you should always try. I mean, I wish everyone scored well. Okay, but it is not the case. So you should try. Yeah, if you don't study, how can you expect to get good grade? Okay, studying in the sense not like you wait till the last minute and try to cram up all the equation. You don't even have to do that. All the equations are given in the formula sheet. Okay, that's you have to study continuously. Like I'm saying now, you have to listen to me carefully. There are certain definitions. You have to understand the definition, understand the concepts. The formula, there is no need to cram the formula at all. Okay, because it's given in the formula sheet. You only have to understand it, make an effort to kind of, okay, memorize it once. If you don't get memorized, you don't have to worry about it at all because it is given in the formula sheet. So that ease your stress, tension, you will study more effectively. Okay, I digressed. Let me get back to the lesson. So I'm talking about this, right? So if delta V will be negative for a positive charge, because positive charge will move from high potential to low potential. That means final is small, initial is big. So the final minus initial will be negative. So that tells you the delta PE will be negative as the charge moves in a conductor. Positive charge. Negative charge is the same thing. Negative charges move from low potential to higher potential, okay, unlike the positive charge. That makes it positive, but the Q is negative, so the whole thing will be negative. So again, the delta PE will be negative, meaning potential energy decreases as the charges move. The power delivered to the circuit element is the energy divided by the elapsed time. Power is a concept that we have defined before in mechanics. So power is how fast the energy is delivered, the rate of energy transfer. We'll come back to the power again, but here we just define it now. So in a circuit, what happens is power is delivered because the potential energy of the charges decreases. Where does it go? It is delivered to the elements in the circuit. Right now, we then section 2, we look at in detail about the current and how the current is related to the motion of the charge carriers. Charge particle, let's say charge particle like in the picture here, is moving through a certain volume, and the cross-sectional area of that volume, let's say it's a circle like that, and we wait for the charges to flow and wait for a certain time period delta t. And if it has a certain speed, an average speed of Vd, we call it the drift speed, then the length it travels through this volume will be delta x, and the delta x is equal to v velocity, the average drift velocity, or we call it drift velocity multiplied by the time. So you understand that, okay? That is the average. What is the definition of average speed? Delta x divided by delta t. So that means delta x is equal to average speed multiplied by delta t. Okay. Now, I can get the volume of this region. The volume will be cross-sectional area multiplied by the length, right? That is how you get the volume of a uniform cross-sectional area. If you know the cross-sectional area, you multiply by the length, it will give you the volume. Now, let's say N is the number of charge carriers per unit volume. In this material, the density of charge carriers, that means number of charge carriers per unit volume, is given by the letter N. N stands for the charge carriers per unit volume. So if I multiply that density by the volume, you will get the total number of charge carriers, total number of charge carriers. So that is fairly straightforward, right? Jude?
Yes, doctor.
Abdulaziz, are you with me? Okay, you can type or you can speak, fine. I hope so. Right, thank you. So now we got this equation. This is the number of charge carriers. You multiply the charge of one charge carrier, that will give you the total charge for that period of time that crosses that cross-sectional area. So this is the number of charge carriers. Let's say Q is the charge of one charge carrier. That will give you the total amount of charge that passes through that area A. Then I will divide both sides of this equation by delta T. I'll tell you why I do that. So that will give me on the left-hand side this one, and delta X divided by delta T on the right-hand side. So now you can see this is what? This is the current. And what is this? This is the drift speed. So now I got this very nice relationship between the current and the drift speed. Drift speed is the average speed of the, say, the charge carriers moving through the conductor, and it is related to the current I through this equation. Of course, we expect the current to be related to the speed, because current is the rate of flow of charges, how fast the charges are moving. So it has something to do with the speed of the charge carriers, obviously. So now we got the equation between the current and the drift speed. The other terms are N is the charge density, how many charge per unit volume, and Q is the charge of one charge carrier, and A is the area of the cross-section through which the charges are flowing. Very nice. So this is another equation. We define the current. Now we got the relationship between the current and the drift speed. Again, you don't have to memorize this, but at least you should know there is such an equation where the current is proportional to the drift speed. Okay, at least you should know that part. All the items are proportional directly. There is no division terms here. Okay, right. So let us move on. Okay, we are just continuing with that relationship. If the conductor is isolated, the electrons undergo random motion. See, this is why the drift speed is not going to be very big. Actually, it is less than a millimeter per second. The drift speed of these electrons, say the charge carrier in a conductor is a negative charge electron, and the speed with which they move of these electron is very small speed, very small. It's a fraction of a millimeter per second. Okay, but when you set up an electric field in a conductor, yeah, it creates an electric force and the electrons and hence a current. Okay, now I'm going to ask you a question. When you, let's say you have a circuit, I'll come back to this question again and say there's a switch and a bulb. This is a bulb. When you turn on the switch, you will see the bulb is lighting up instantly, almost instantly, immediately. There is no time lag. And the current is related to this drift speed. And I'm saying this drift speed is very small. I'll explain why it is small. But it doesn't kind of make sense. Okay, how come if the drift speed is so small, we get the bulb lighting up the moment we close the switch, almost instantly? I'll come back to this question again, but just have it in mind. Okay, we will discuss this again. Now, about this charge carrier motion in the conductor, say electron, if there is no electric field, these electrons, the free electrons in the conductor will be moving haphazardly, okay, in all directions, randomly. So there is no net motion in any direction. This means if there is an electron moving to the right, okay, so there will be another electron moving to the left, so it get cancelled. Okay, on average, there is no net motion in any direction. Okay, yeah, do you understand what I'm saying? When there is no electric field. So, but if you apply an electric field by connecting a battery, for example, let's say you apply an electric field to the left, like in this figure, and this electron being a negative charge, it will experience the electric force in the opposite direction, because you know the relationship between electric field and the electric force is this. So if Q is negative, the force will be in opposite direction to the electric field. Q you should substitute with the sign. The negative sign will flip the direction of the force. So now let's say we have an electric field to the left. Electron will experience a force to the right. So it is try to move the electron on average to the right. But as it moves, it is going to hit other electrons and their atomic lattices. It will be hit and it will try to redirect. Okay, it will bounce back maybe even in the opposite direction or perpendicular and so on. So maybe there is one electron coming like that, it will hit with another electron, it can be reflected back. But however, since there is an electric force trying to make it go in the right direction, there will be a net motion of this electron in the direction of that electric force. That means in the opposite direction of the electric field. So this is the reason why this drift speed, the average speed of the electron when an electric field is applied, is going to be very small. It is like fraction of a millimeter per second. Okay. So the net motion of the electron is in the opposite direction of the electric field, and it will be very small value. Now having said that, now we have we are going to visit this link. I'm going to copy this link and going to post in the chat box. Then you can click, you also should click on this link. How do I copy this link? Let me see if I can post it in the chat box. Oops, why is it not coming? Okay, got it. enter, right. So can you see this link in the chat box? Please click on that link. It will open your browser and you'll go to a certain page, which will look like this. Are you all with me? Please, it's like a lab, a virtual lab, okay? I want you to do that. Click on that link and it will take you to this page, and click on this play button. Or you may even download, and probably it is faster. But anyway, just click on this link and it should open soon. Taking some time. This computer is slow. All right, there it is. Jude, are you with me? What about the others?
Yes, doctor.
Okay, let me ask other people as well. This is not right. You know, you should participate. Okay, I'm really going to make participation score. If you don't participate, you're going to get 0 for attendance. Dima, where are you? Can you answer me? Okay, did you open the link? Please try, yeah, thank you, Dima. So do it with us, okay, with me. Let's say you click on the intro, okay, now the lab, and you will get something like this. Okay, it doesn't matter, intro, lab, I don't know what the difference is, but anyway, now I have clicked the intro, you will get this screen. Now here, it is like a lab, okay, so you can grab things, and I want to construct a circuit. Please do with me. Grab a wire from the left side here and bring it to the middle. And we have got a wire. We can stretch the wire, shrink the wire. Okay, that's okay. Then grab this battery and take some more wires. Okay, right. One more wire, connect to that, turn it around. It's fun. Okay, please do it. And then like that. Okay, maybe shrink a little bit. Now you're going to take a switch. Okay, switch is an important component in a circuit. It's a safety thing. Should always have a switch, so you don't accidentally connect the circuit. You always connect the circuit, close the circuit only when you want it. Take some more wires. Okay, right. Now take the bulb, electric bulb. So it has two ends to the bulb. You know, bulb has two ends, right? I mean, it is not obvious because you only tighten the bulb, but you know, it has two ends. And it current flows through this end and come out from the other end. Now I'm going to continue this, take another wire and then deflect it down, take another wire, and there it is. So I have got a very simple circuit. I hope you're also doing it with me in your own browser. Right. So it's just a simple circuit. Circuit mean round, okay, circle, circuit. So if you close this switch, by clicking on the switch, it will close. You know what will happen? Current will flow through the bulb and therefore the light will come on. Nice, almost like real, almost, okay. So did you do that?
Doctor, isn't this direct current?
I'm sorry, can you say it again?
Isn't this direct current?
Dioc?
Direct current, DC.
Direct current, yeah, direct. Yeah. What about it? I didn't quite.
But I'm asking, isn't this like an example of direct current?
Oh yeah, it's direct current. Yeah. Okay, you are talking something that you. All right. Yeah. Direct current. Direct current mean a steady current. Okay, that is the meaning of direct current. The battery supplies a current which is steady, meaning a constant value. Okay, so that is the meaning of direct current. It's a direct current circuit. So we'll always start with a direct current, then we'll go to the alternating current. Okay, that's fine. Okay, nice that you brought it up. But anyway, yeah, it is direct current. So for the others, okay, what do you mean by direct? The steady current, a constant value of current. The battery supplies a steady current. So it's a direct current. Now, so but the word is a bit misleading, direct. meaning steady current. Okay, fine. Okay, right, it's worked. Thank you. Now, it's a very simple circuit, a battery and a bulb. So close it, the light comes on, open it, everything stops. Now, the question I'm going to ask you here is this. When I close the switch, you see the bulb comes on immediately. But I said the drift speed of the electron is very, very small. Now, how is it possible for the light to come? You already have the answer by looking at the simulation. If you haven't seen the simulation, suppose I didn't show the current. Yeah, I should have done that. Okay, I don't show the current. Close the switch, the light comes on immediately. Open the switch, okay, almost immediately. Doesn't seem, if you suppose the electrons from the negative end of the battery has to travel all the way to the bulb and come back to the positive end of the terminal, it is going to take several seconds. Okay, even if the short path, we know the speed of the drift speed of the electron is very small, like millimeters or even less than a millimeter per second. And it is going to take a long time to make that journey through the circuit. But actually, the moment you close the switch, the bulb comes on. Now, you know the explanation now. What is the explanation? Show the current, then you will know the explanation. Do you see the explanation? Jude, okay, I have got an answer. Because yes, yeah, exactly, Abdullah. Because the electrons are charged everywhere along. What has to travel is not the electron from the battery to make the journey around. The moment you close the switch, the electric field from the battery is felt everywhere, not instantly, at the speed of light. Electromagnetic wave, electric wave, okay, electromagnetic wave. The electric field is an electromagnetic wave. The moment you close the switch, the electric field is set up at the speed of light. You know what is the speed of light? Electromagnetic wave. Light is an electromagnetic wave, you know that, right? The speed of light is 300 million meters per second. 300 million meters per second. So this is the fastest speed possible. So that's why it looks like almost instantly. You don't need this particular electron, say this particular electron to make the journey and come back. You know, you close the switch on, the electron already there in the bulb will start moving because the electric field is felt everywhere instantly, you know, not instantly, at the speed of light, okay, right. So it's now very clear. That's why I wanted to come to this simulation to show that. Suppose you don't show the current, the electrons, you know, it is not obvious, but with this simulation, you can answer this question, you know, you understand very easily. So it's a very nice simulation, okay. We'll come back to this again. So let me go back to the slide and start the presentation. And we will come back to visiting this again, okay, for different things. Right. So we saw that. So let me read through this now. Electrons in the bulb move in response to the electric field set up in the completed circuit. Okay. The battery supplies energy. It's not that it supplies electron, right? So you should understand. It just supplies the energy as an electric field being set up in the whole circuit that moves the electron everywhere along the circuit at the same time. So that's why it is that fast. Okay, so in the second slide, continuing, the drift speed is much smaller than the average speed between collisions. See, why the drift speed is smaller? Because the electrons can be moving very fast, but the thing is, it's going to hit other electrons, the other lattice atoms, so it will be deflected. It wants to go to the right, but it is constantly being deflected, okay? It is being changed the motion. So that's why the drift speed is small. But we don't, it doesn't matter to us because the electric field will be set up at a very great speed. It is felt everywhere at the speed of light. You can see the value. It's 10 to the minus 4, meaning 0.1 millimeter per second. 10 to the minus 4 meters per second mean 10 to the minus 3 is a millimeter, right? 10 to the minus 4 will be 0.1 millimeter. Okay, but what is the speed of light? How fast the electric field is set up? It is at 10 to the power 8. You can see the huge difference. Right, circuits. Now, what is a circuit? A circuit is a closed path of some sort. It doesn't have to be a circle exactly, but a closed path of some sort around which current circulates. So circuit means circle, round, okay, going around. Circuit diagram can be used to represent the circuit. Okay, you don't have to actually draw, battery like a battery and so on. We have symbols for these circuit elements. A battery is represented by two lines, one short and large. Short line is the negative, the large line is the positive, and so on. So we can use these symbols to represent a circuit diagram. In circuit, the quantities that we are interested in are current, okay, and voltage or potential difference, okay, it's also called voltage. In electrical engineering or in circuit in general, we use the voltage, but it is actually the potential difference. Right, so we have a circuit here. Okay, we're going to go back to our simulation and set up this circuit. We have already done the circuit, the battery and the bulb. You have it already set up, okay, the battery and the bulb. But they have got additional thing here. What is called the voltmeter. You should understand, you know the meaning of meter. Meter is something that measure, right? Measuring, meter. Meter mean measuring. So voltmeter mean measuring voltage. So that's a device that measures the voltage. So we call it voltmeter. And then we have this one. You can guess what it is. Is the ampere meter, because we measure the amperes, the current. So, but we don't say ampere meter, we call it ammeter. So, yeah, again, I'm losing you. I don't know. Are you listening? Abdullah? Okay, right. Gala, thank you, Gala. So, ammeter measures the current and voltmeter measures the voltage. Now, let's go back to the simulation in the website, and let's connect the voltmeter and ammeter and talk about it a little bit more. Here it is. Now on the right hand side we have got voltmeters and ammeters that can be hooked to the, let me start with the ammeter. This is the ammeter. Ammeter has two ends, the negative side and the positive side, and we can connect the ammeter to this circuit. My target, I want to know, oops, I rather prefer the other ammeter. Let me use the lab, okay, so, oops, now I have to construct the circuit again, because in the lab has the ammeter that I need with the positive and negative sign. This is a special kind of ammeter, but I prefer this ammeter with the two ends. So that's why I clicked on the lab. So I have to construct the circuit again. I can do it quickly. Battery, switch, another wire, stretch it and connect it. Maybe another wire to keep it nice. Another wire, another wire, and turn it around, and the bulb, another wire, and there we go. Right, my circuit is ready. Okay, now I want to know, when I connect the circuit, I want to know what is the current flowing through this bulb. I want to measure for some reason. So I should connect my ammeter such that my voice is lagging. Okay, I don't know, probably your connection. Okay, well, I can't do anything. Okay, you have to fix it from your side. Okay, right, never mind. So I want to listen carefully. Okay, I want to measure the current through the bulb. Say, let's say, well, I don't know what the current is. I also want to measure the voltage or the potential difference across the bulb. That will be actually, because we have only the battery and the bulb, whatever the voltage of the battery will appear across the bulb. So to measure the current, let me start with the current. I need to connect this circuit in series with the bulb. In other words, I should connect it, okay, let me stretch it a little bit. I should connect it here. So whatever the current that flows through the bulb should flow through the ammeter as well. So that means, in other words, let me cut this, okay, connection, so it is free. I should put it, whatever the current that flows through the bulb will flow through the current. So if I do this, it's fine. So now it is the way I wanted it. So whatever the current that flows through the bulb will flow through the ammeter also and come back. Let me switch it on, then you can see it is, switch it on. Yeah, see, it says 0.9 amperes. So the charges that flow through, it is in series. The ammeter is connected in series with the bulb. So the charge that flows through the ammeter is flowing through the bulb as well. You remember when we talked about capacitors in series and in parallel? So when you want to connect the capacitors in series, you connect end to end. So that's what I did here exactly. So the ammeter is connected in series with the element through which you want to, the element in through which the current is flowing, and you want to measure the current through that element. So the bulb is what we are interested in. So whatever the current that flows through the bulb is also flowing through the ammeter. So we are measuring the current through the bulb. Simple, obvious, right? So this is, you have to connect the ammeter in series with the element you are interested in of measuring the current. Okay, good. Now what? I also want to measure the voltage. So voltage is measured by this guy, which is a voltmeter. So the voltage is measured by tapping the 2 points across which you want to measure the potential difference. So potential difference means 2 points, A and B. What is the potential difference between the 2 points? So I want to measure the potential between the two end of the bulb. So one end, so the positive end, okay, the voltmeter, like the ammeter, also has positive, negative, okay, the end has positive side and the negative side. So you take the positive end is usually red, okay, take the positive end and connect it to the positive side of the bulb, because now this is the battery positive side. So the positive side of the bulb will be this guy, and the other end you connect to the negative end of the, there it is. It's measuring 9 volt. It is exactly the potential difference of the voltage of the battery, 9 volt, because we connected a 9 volt battery. So it's measuring 9 volt. So you can see that it is connected in parallel to the bulb. Okay, now it is, things switched. doesn't matter, then it will show as the minus 9 volt. That's why, because you have to put the positive to the positive and the negative to the negative end. But I just want to demonstrate the parallel connection. Okay, you are connecting the voltmeter in parallel with the element, the bulb. If you want to measure the voltage across something, you have to connect the voltmeter parallel to that something. Is that clear? Ammeter should be in series and the voltmeter should be connected in parallel. Okay, let me open the switch. Okay, I don't want to drain the battery. Okay, right, let me get back to the slides. Okay, here we go. Now in this diagram, you can see the ammeter is connected in series with the bulb and the voltmeter is connected parallel to the bulb. Good. So let's continue. Go to the next slide. Ohm, George Ohm. It's a physicist who worked, experimental physicist who worked in electricity. He lived in this era, in these years. He formulated the concept of resistance in regard to electricity, what is called resistance. Now, what is resistance? Let's see. He discovered when you take a bulb, let's say, and you apply a certain voltage or potential difference between them, a current flows. That current is proportional to the applied potential difference or the voltage. You increase the voltage by putting a battery with a higher voltage, for example, you get a bigger current flowing through the bulb or the resistance or whatever that element. So he discovered this proportionality: more voltage, more current; less voltage, less current. Okay, so that's why there is a law after him called the Ohm's law. Let me go to the next slide. He defined the resistance as the voltage applied across the element divided by the current through that. This is the resistance. This is the definition of a resistance of a material to which I apply a potential difference delta V, and I measure the current, and the ratio delta V potential or the voltage divided by current is equal to its resistance. Yeah, the constant, because I said it is proportional, it is not proportional for all material. For certain material, it's proportional, and we call that quantity R as the resistance. Resistance is equal to the potential difference applied divided by the current that flows through it. And what about the unit for this? Let me probably look at the next slide. Okay. Voltage is in volt and current is in ampere. So the unit will be volt per ampere. But however, as it always happens, usually happens, we don't want to call it volt per ampere. We have one symbol for it. We call it ohms. After the person who discovered this, Mr. Ohms, so we have the symbol omega, okay, not the letter O. This is a Greek letter. It is called omega. The Greek letter omega is used, but we call it ohms. We don't call it omega. So 1 volt per ohm is 1 ohm. After that, scientist who worked on this, who discovered this relationship between potential difference and the current. Now, this is the Greek letter omega. We also have another omega. This is also called omega. It looks like a W, but it's omega. Why do you have two letters for the same character omega? Anybody can answer that? These are Greek letters like Roman letter. Say for example, A, we have two symbols for A. What is the difference between them? It's exactly the same thing. This is the capital omega in Greek alphabet. This is the lowercase or simple omega in Greek alphabet. Okay. I hardly see anybody showing any interest. Am I talking to myself?
No, doctor, everything's clear.
Clear? Okay, fine. Thank you. Right. Okay, so that is resistance. It is volt measured, SI unit is volt per ampere, but we have the letter omega, which we call ohms. We don't call it omega. So 1 ohm is actually 1 volt per ampere. Resistance in a circuit arises due to collision between the electrons carrying the current with the fixed atoms and the other electrons inside the conductor, mainly the fixed atoms in the conductor. Okay. Ohm's law. Now, that was the definition of resistance, but at the same time, people started saying it is a law, but it's actually not a law, it's a definition. But it seems to be, there seems to be the value of resistance is a constant, so we can say it is a law. The delta V is proportional to I, the proportionality constant R. If this R is a constant, it's a proportional constant. It's not so, but for certain materials, many materials, including most metals, the resistance remains constant over a wide range of applied voltage. Okay, it's again, it is not constant for large voltage, but so they thought, okay, it's a law because R is a constant. So it came to be referred to as the Ohm's law. But you should remember, is actually, you should take, strictly speaking, is just the definition of resistance. Okay, but since it seems to behave, the R seems to be a constant for certain material, it came to be referred as a law. But actually, it's an empirical relationship that is valid only for certain material. And we say any material that obeys Ohm's law as ohmic devices. So here we see a graph where R is a constant, because here we can take the delta V over delta I. This is delta V, and this is I. Okay, I in the y-axis and delta V in the x-axis. So we can see it's a constant. The ratio delta V over I, delta V over I, because a straight line is a constant. So the slope, it is delta I over V, because I is in the y-axis. Therefore, slope is equal to 1 over R. If you draw I in the y-axis. If you switch it, if you draw delta V in the y-axis and I in the x-axis, then slope will be the R. So this is a particular thing that obeys the Ohm's law for an ohmic device, because we get a straight line. That means R is constant. Slope is not equal to the resistance, but is equal to 1 over resistance, because I is in the y-axis. Now in this graph here, it is not a straight line. It is a curve. Okay. So now if you take the resistance, at this point, it will have a certain resistance. As you go another point, the resistance, it is decreasing, right? Well, slope is increasing. That means resistance is decreasing because it's 1 over R. So this is a non-ohmic, because this device doesn't have a constant value for the resistance. So it is a non-ohmic material. It's a curve. The current voltage relationship is nonlinear. An example of nonlinear device is diode. Okay, diode is something that that we have in circuit, electronic circuit. We'll not deal with it now. Okay, if you are doing electrical engineering, you learn more about diodes later. Semiconductors, diode is a semiconductor. Semiconductors are non-ohmic devices. They don't have a constant resistance. Now we are going to define another quantity. It looks like resistance, right? It's not resistance, it's called resistivity. What's the difference? Let's see what the difference is. Okay, let's take a wire, a conductor, metallic wire. Oops, what did I do? And say copper wire. So a piece of copper wire, say length is L. Then another copper wire of the same thickness, okay, but the length is doubled. I double the length. I measure the resistance of this small short wire. Let's say I get 10 ohms. When I double the length, I get 20 ohms. Okay, this is experimental fact. So I say the resistance is proportional for a given material, copper wire. Okay, not another. I don't change the material, same copper. It is proportional to the length. So that's experimentally observed. Okay, it's proportional, linearly proportional. When you double, resistance also double. So that you can say that, right? Fine. Then I do another experiment. I take the same copper wire of length, but this time I don't change the length. I change the thickness. I make it thicker. Same length. Oops. The same length, length is fixed, but here area, cross-sectional area A1, now I have double the cross-sectional area. You see what happened now? The resistance become half. Say if the resistance is 10 ohm here, now the resistance become 5 ohm. When you double, the resistance become half. So what can I say now? The resistance, if you keep the length fixed, you can see it is inversely proportional to the area. Are you following me? Okay, right. Now I can put them both together. I can say resistance is proportional to the length, but inversely proportional to the area. And the proportionality constant is this rho. So resistance is for a given material is proportional to the length, inversely proportional to the area. And the constant is called rho. And again, it's a Greek letter. It is spelled RHO and pronounced rho. Okay. Resistivity. It is not resistance, it is resistivity. Okay. So resistivity of a material is a constant, a given material. For copper, will have a certain value for resistivity, and aluminum, another metal, will have a different value for resistivity. Okay. So good conductor will have a small resistivity, smaller resistivity. What about the unit? You can show by moving it around. The resistivity has the SI unit ohm meter, not ohm meter. Resistance has the unit ohm. Resistivity has a unit ohm meter, ohm into meter, not ohm per meter. Okay, good. So now let's go to the next slide. We have a question. So let's do this question on resistivity. Calculate the resistance per unit length of a 22 gauge. This is pronounced gauge, okay? Spelled G, but it's gauge. It's just telling the thickness of the wire in some standard, okay? We don't have to worry about that. So different gauges mean different thickness. Nichrome. Nichrome is a mixture of two metals, I think, maybe nickel and chromium or something. So it is nichrome. Yeah, I think so. So it's not a pure element, it's a mixture, alloy. wire of radius 0.321 millimeter. So we are given what the material is, it's nichrome, and the resistivity of nichrome is given at the end of the question. Part A of the question is calculate the resistance. Not just resistance, he is saying resistance per unit length. He wants to get this. Now, how do you think we can get the answer? Anybody want to help me? Resistivity is given, so you should give us a clue. So it has to do something with that equation that we learned just now, relating the resistance to the resistivity, right?
We use resistivity? Yeah, do we use that?
Yeah. Yes. See, and you bring it to this side, what you get? R over L is equal to resistivity divided by. So he's asking for not R, because length of the wire is not given. So he's asking for the resistance per unit length. In other words, he's asking for R over L. And resistivity is given, area can be found because the radius of the wire is given. Radius means, you know, wire is a cylinder, right? A thin cylinder. So the cross-sectional area is a circle. So the area of a circle is pi r squared. So if you know the radius, I know the cross-sectional area. So the radius is given. So now it's a matter of substitution. Rho is here given 1.5 into the minus 6 is already in SI units, so you don't have to worry about it. Divide by what converting. A is the cross-sectional area of a circle is pi r squared. The value of r is given, but it is in millimeter. You have to convert it into meter and square it and put it there. You get the answer. Done. Okay, please do it. Okay, I'm not going to do it for you, but I showed you how to do it, and you should be able to do it. Okay, let's go to the part B. Erase. Part B is a continuation of that. If a potential difference of 10 volt is maintained across this 1 meter length of this wire, what is the current in the wire? So we take this wire and we have found the resistance per unit length for this wire, but now we're taking 1 meter of this wire. So it can substitute, we already got this value in A, right? Let me call it X. I have a number for X from part A. So I know the resistance of this wire. And I apply a potential difference of 10 volt across this wire. Can I find the current? The question is find the current.
Can you use Ohm's law?
Yes, exactly. Very good. So see, you have to be able to see, if you are paying attention like Jude did, okay. So whenever I ask the question, you just make the connection very quickly. So because now current is the question, we know the resistance and the potential difference is given in the question. So we know there is an equation because the ohmic device, we have the Ohm's law, delta V is equal to IR. The definition become a law now, okay, because R is a constant, we know R, okay, there is the value X because it's 1 meter length and we put the resistance per unit length in part A. So we have this. We are given this, you are asked to find I. So just a matter of substitution and finding the answer. Very good. Okay, right. So I think I'm going to stop. I'm not going to do the last part. I will stop now. I want you to do the part C. It's a slightly challenging. We need to get to have some common sense here to do that. It looks like, out of the material I taught you, but it's just some general knowledge here to answer.
For doctor, for question number C, do we use the resistivity equation? The one where R equals to the rho L over A?
For C, you mean part C?
Yeah, I'm asking.
Not really. Okay, since you are insisting, I'll give you a clue. Okay, good. Fine. Let me. What is the question? Part C. The wire is melted down and recast with twice its original length. Find the new resistance. So we have this wire. Okay, it has a certain length, which is 1 meter, and it has a certain area, which is the radius. Okay, we have a certain radius R1 and the corresponding area. So we have certain length and certain radius. Now we take this piece of wire, and let me call it L1 R1, and recast with twice its original length. So I recast, I hope you understand, you melt it, okay, become a liquid and form the same material. We don't add anything, okay, the same volume in that sense, okay, but we stretch it, right? We make the length twice long, so it will become thinner, right? L1 become 2L1 and A1 will become A2. We don't know what it is. We made the length twice, so that means, of course, the same amount of material, the same volume here, right? They are both the same volume. So A1 will become A2, which is smaller than A1. Did you follow that, Jude?
Yes, doctor. So basically, area changes as well.
Yeah, now I told you it is the same volume, right? So that means A1 L1 is the volume of the first case and A2 L2 is the volume of that. We can say this, A1 L1 is equal to A2 L2. So this is what the common sense I'm talking about. So the new volume is equal to the old volume, A2 L2 is equal to 1. And you know that L2 is twice L1. So I can, for this, I can write pi R1 squared L1. This is pi R2 squared L2. Pi cancel with pi. So L2, I can write 2L1. So L1 cancel with L1. And then you will have R1 squared is equal to R2 squared times 2. Is that right? Okay.
Yeah,
Yes,
right.
I hope I didn't make any mistakes. So now we get a relationship between the two radii. What is the question? Find the new resistance. The new resistance, new, will be equal to, no, rho doesn't change, it's the same rho, right? L1, L2 divided by A2. This is the new resistance. So, I mean, I don't have to do all that. I don't have to make it into radius. So I can, let me, there is no, let me, here, I can write A2 is equal to L2, A2 is equal to, okay, let me go like this. A2 is equal to A1, L1 over L2. So A1, L1, L2 is 2L1. So here get A2 is equal to A1 over 2. I hope I got it right. Okay, yeah, A2 is equal to here you substitute for L2 as 2L1, A2 as A1 over 2. So you can get the new resistance in terms of the old resistance. I'll stop there, okay? You have to do some part of the work as well. Right. So I will end now. So let's continue from here in the next class. We'll be able to finish the whole lecture in the next class, whole chapter in the next class. So now then we'll be getting ready for the exam number 2. Okay. See you in the next class. Thank you.
Thank you, Dr. Avanis.
You're welcome.